I imagine everyone who's still up at this late hour has heard about Ethernet and TCP/IP and communicated with it. And if you've ever done so, you will have realized a few things. The most important thing, I think, is that encryption and anonymity is always something duct-taped to it. You make a config mistake, you are not careful in any way, shape, or form, and suddenly that what is supposed to be an encrypted transmission is just going over the network, willy-nilly readable for everyone. Also, have you ever tried to run normal TCP/IP over a network that is a bit, say, icky with the transmission speeds and the packet losses? Mark Quist and his probably by now quite large team of contributors has started 8 years ago to implement a network protocol that could be feasibly run over Morse code. Like you could sit there and within spec communicate to someone over like this beeping button. Also, it has encryption built in, so you cannot communicate unencrypted by accident. So I would like to hear a warm round of applause for Reticulum, Unstoppable Networks for the People by Mark.
All right. Thank you very much for the introduction. I'm Mark, and I'm one of the developers of the Reticulum project. So, as you so aptly put it, we're all familiar with TCP/IP and the whole stack built around this. So what is Reticulum? Reticulum is a networking protocol. It's also an internetworking protocol. And it attempts to solve the same problems that we're familiar with, namely getting any kind of data reliably from point A to point B, either directly or over any number of hops. But it uses cryptographic principles for addressing and data transport instead of arbitrary number assignments. Currently, it has a fully functional, well-tested and stable reference implementation. And this implementation is called the Reticulum Network Stack. It's released on the MIT license, and it's available both in the package format and as a source code. And you can grab it by going to reticulum.network, where you can also access the documentation and specifications and the full manual for the project. So, what are the primary problems with the current communication stacks we have today? One of them is that nobody actually really talks to each other anymore. This is quite strange because even our most basic compute devices have really advanced capabilities. We have lots of processing power, we have large amounts of storage and memory, and most devices even have advanced radios and communications hardware built in. Yet, if I want to send a message to any one of you in this same room, or a friend in the next building, this strange scenario occurs automatically. My communication goes through an ISP, a couple of countries, and some quite questionable intermediaries, and then probably another country, and then it ends up at a server somewhere else. And that's a server I don't control, and neither does any of the other people that actually use the communication control this server. The data is then run from that server and, well, more or less through the same kind of possibly quite questionable data path until it finally reaches my friend Tom there in the end. And when you think about it, this situation is actually pretty bizarre. And it's quite strange that we've grown so used to it. Some applications try to alleviate this by, for example, using technologies like Bluetooth and other existing technologies. But ideally, it should not be the job of the application developer to solve this. It should not be something that's plastered on as an afterthought. It should be something that the networking protocol itself is able to handle. And the networking protocol should be able to get data from point A to B in the most efficient way, and ideally without having to involve any unnecessary intermediaries along the way. So our devices are perfectly capable of using peer-to-peer communication, but they don't. Another quite fundamental problem is that if you need somebody else's server to communicate with the peers that you want to communicate with, or to disseminate any kind of information, the people that run those servers or services effectively own your action potential. And they can take this action potential away at will if they don't feel that you comply with how they want to run things. So this is, in my opinion, a very unwelcome power balance. And in terms of compute power and storage and where our technology is in all kinds of other regards, it's also quite unnecessary. Most of the current attempts to re-establish end-to-end connectivity between compute devices are exclusively overlays to the existing internet protocol stack. And this can definitely work. It does work very well in many cases, but it still inherits all of the problems that are inherent to IP. For example, that it doesn't have any native encryption built in. And it then tries to work around them. And in that process, it creates even more overhead than the whole IP and TCP and HTTPS and so on stack introduces in the first place. And when you get to that level of overhead, this effectively excludes a lot of scenarios. For example, communicating over low bandwidth radio protocols that are often very long range, but low bandwidth. Also scenarios like disaster relief and resource-constrained environments, and many other adverse scenarios where you have people that would rather you not communicating than actually being able to effectively establish communication with other people and systems. So writing decentralized and self-sovereign applications on top of IP is very hard. And that's mostly because 90% of the work you put in to doing that goes into making IP do things that it was kind of accidentally designed not to do. Another problem we find ourselves in is that the base layer infrastructure that run the internet and therefore more or less all communication that we have access to is inherently centralized. So it might be that in essence the internet is comprised of a large number of autonomous systems and these are internet-worked together. But to have these so-called autonomous systems internet work, you still need the blessing of very large and very strictly governed and controlled bureaucratic structures and hierarchies. You can't just go out and grab a range of addresses and decide to peer them with someone of your choosing. You can do that, but they won't be reachable for the rest of the internet, or the rest of the world for that matter. So if the current base layer infrastructure is not fixed, it's at least about as dynamic as slow-flowing tar. So it's very difficult to change addresses and change topologies and topographies of networks once they do exist. But ideally, we want to be able to just create endpoint addresses that are globally reachable, and we want them to become reachable in a few minutes instead of days or weeks. And this leads to another strange situation, which is that you never really own your endpoint addresses. You might be able to gain access to them, but they're not yours. They can be taken away, and they can be blocked quite easily as well, because routing to them requires that everyone along the path agrees that they should be routable and you should actually be able to be reached. So right now, to be able to have reachable endpoint addresses in a network, you need to trust a whole list of intermediaries. You need to trust base layer infrastructure providers. You need to have public IP address providers. You need to trust DNS providers, SSL certificate authorities, and signing intermediaries. And most likely, you will also need to have hosted server infrastructure or trust other kind of service providers. And in 99.9% of cases, this will effectively exclude normal people or organizations from running their own communications infrastructure and hosting their own truly sovereign platforms for communication and disseminating information. I think this is inherently broken. So we're basically fucked, because in reality we all need to use someone else's server to disseminate any kind of information or coordinate action. And that's really one of the important points, because without communication between peers, between people, we can't effectively coordinate action and effectuate change. So if we try to imagine a situation of open communication systems, what would that look like? What would we need to have a system of networks that did not impose these limitations? I think one of the primary factors would be the need for true end-to-end connectivity for everyone. So everyone needs to be able to create addresses that are reachable by everyone else. We also need mandatory end-to-end encryption at the base layer, not as something that's plastered on as an afterthought on top of all of the other layers of the stack, but something that's inherently and fundamentally built in and cannot be switched off. Another very important point, I think, is that we need initiator anonymity at the base layer. So anyone that wants to communicate, to either disseminate information or to obtain information or to communicate with other people, needs to be able to do so in a way that does not reveal their identity necessarily unless they want to. We also need to remove the requirement of having arbiters and hierarchical structures to be able to associate and deassociate network segments that want to be able to communicate. And we need to do so without any pre-coordination necessary. So ideally, we should only have the base knowledge of how to physically connect with a workable carrier between networks, and they should be able to interoperate and internetwork between each other without having had to pre-coordinate address spaces and segments. This should just happen automatically once you do it, whether it's like 2 days or 25 years in the future. We also need self-sovereign address assignment at will, without interacting with any kind of governing structures or gatekeepers. And quite importantly, we need to lower the barrier to entry to actually create the base layer infrastructure and create the workable links over any kind of medium that we have available to us. And right now, it's not like realistically possible in any way to coordinate some kind of massive shift away from IP-based networks. And it's not really desirable to do that anyways, because we have lots of good systems and lots of important systems that run on top of these networks. And there's no point in throwing that out. So I think for any technology in this kind of way to be successful or usable, we need to have a situation where isolated networks and also isolated small-scale networks are completely functional and provide real value to their users without the rest of the world necessarily having to care about it. And such isolated networks, they must be able to dynamically converge into larger networks if paths between them become available. And as I said before, this must occur automatically without requiring any oversight or user intervention. And it should also be able to coexist with and bridge over the already established infrastructure and protocols that we have. So I think if we can get to a point where these prerequisites or requirements are fulfilled, we can have networks that can be created and grow organically and over time form larger and much more useful networks as well. So how does Reticulum try to solve these problems? They're quite fundamental and some of them are quite hard to do. But if we start with the paradigm of address assignment and addressing, we can look at how Reticulum manages this. So basically we completely throw out the idea of having some random authorities assign specific hierarchical number structures as endpoint addresses. And instead, we use well-known and well-tested cryptographic principles to do this. So the gist of it is that to create any kind of address in the network, we create a ED25519 and X25519 key pair. We derive some public keys for that, mix in a destination type, and we can now deterministically get a destination hash for this construction that we can use as an address in the network. And to disseminate that information, we simply sign it with we sign the destination hash together with some more verification data and the public key, and transmit this onto the network. And this information can then be used by any other peer in the network to establish the initial communication with another endpoint. And furthermore, any routing nodes, called transport nodes in Reticulum, can use this signed information to verify routing paths towards the endpoint destination. It's also important to note that nobody requires full network, full topological knowledge of the network for this to work. You basically only need to know the current best estimate of the best hop towards the destination for this to work. So it's quite efficient. So to recap that, we have a cryptographic identity that consists of a secret private key that will never leave your device or the system. From that we derive some public keys, and we can mix in destination types to create many different destinations from that one identity. And this can be quite important if you have an application that requires multiple types of endpoint addresses to be reachable, but you still want these to be linked to the same identity. For example, in the context of messaging applications, or in situations where you want to remotely manage machines or other kinds of systems. So the destination announcers that we send out on the network, as I talked about before, are comprised of a very lightweight construction. They'll usually range in around like 150 to 250 bytes. They contain the destination hash, which is effectively the address on the network. They contain the public key of the destination, some optional application data, a random blob to ensure that announcers cannot be replayed and used to forge invalid paths, and then everything is signed with an ED 25519 signature to verify the authenticity. And that's all well and good, but you of course need some kind of interface to send this out over. So the approach that Reticulum takes here is to have a very flexible and modular interface system that can also be expanded at runtime by users. Reticulum can automatically use any number of heterogeneous physical or virtual interfaces to form a self-configuring mesh. And it works over anything that supports a physical layer MTU of at least 500 bytes, and as long as you have more than 5 bits per second of throughput, it actually works. So it's not even a joke that you could do this over Morse code, because you actually could if you have a fast enough typing speed. Effectively, to do this, most applications, like even low bandwidth applications, will probably target something like 300 bits per second. But that's slow enough that you can run full like messaging and information sharing even over long distance HF radio links, which has been demonstrated and run over Reticulum actually. So this means you can use more or less anything. You can use existing high performance devices like Ethernet, fiber optics, Wi-Fi. You can also use plain old serial lines. You can use LoRa radios. You can use packet radio modems. You can use TCP, UDP, I2P. You can basically use anything that you can throw at it or write an interface driver for. And writing an interface is really quite easy. So can it handle many interfaces? Yes, absolutely. This is like an interface graph of one of the testnet nodes that are running right now. And each of those little purple dots you see is an individual interface. And on this node, there's about 150, I think, different active interfaces that are bridged to all kinds of other systems. And the Reticulum routing core will happily route between those 150 interfaces at will. One of the important things to note here is that the addresses, the destination hashes, are not bound to any physical devices. So addresses live at the application layer, so to speak. So there's no configuration of addresses or subnets or anything like that on the interface level. You can basically throw any number of interfaces at the routing daemon, and it's just going to find out which paths are the most efficient for where we want to get to. And that eases configuration quite a lot. So the packet structure on the raw network is quite simple, actually, and that's a relief, because the overhead is quite low. As you can see, we have a header field, which is just 2 bytes, and that's then appended with a context field. So we have basically a 3-byte header. We have a 16-byte destination field, and that's the overhead. Then you have the payload data. And one thing you might notice that's conspicuously missing from this is a source field. So there's actually no source addresses at all in Reticulum. There will never be a packet that includes information about where it came from at all. And you can, of course, still have bidirectional communication. Even the low-level raw packet API is able to have signed, cryptographically signed acknowledgements sent back. So, but how do you establish full bidirectional communication without any sources? Reticulum uses a concept of quite simple link establishment. So, to get a bidirectional communication link set up with the destination endpoint, an initiator node will first generate a set of ephemeral X25519 keys and send this in a link request to the destination. That destination will then also generate a new set of ephemeral keys. It's going to then sign that information, sign the public key and the derived link identification hash, and send that back to the initiator. The initiator can then verify that the new public key was actually created by the desired destination node and perform an ECDH key exchange to get a new ephemeral key, and then perform the rest of the link setup. And this construction is very lightweight. It only requires 3 packets to be sent back and forth over the network. That's 297 bytes. So again, this works even in extremely bandwidth-constrained environments. And it provides an end-to-end encrypted link with forward secrecy. It also has a very low cost of keeping links alive at only 0.44 bits per second. So this can accommodate quite a lot of links, even in very bandwidth-constrained situations. You can have hundreds of links, even over like 1200 baud packet radio, if you want to. But most importantly, link initiators remain anonymous. There's no information transmitted at any point in this process that reveals where the link establishment request is coming from. And because the network doesn't know about the full topology, there's also no way to track it back all the way to the source unless you have complete control over the entire routing path back to the source. Of course, initiators can identify to the destination once the link has been established. So once the link has been established, you can send an encrypted identification to the destination, which is obviously quite useful for authentication. So we also have authentication built into the lowest layers of the protocol. That's also something you don't need to mess around with yourself, and it ties into the entire identity system built in here. So putting it all together, in its current state, Reticulum provides coordination-less, globally unique addressing and identification, provides full end-to-end connectivity for all destinations on the network, mandatory end-to-end encryption with forward secrecy, and routing unencrypted traffic is simply impossible. It's dropped. It's not possible to send any unencrypted traffic on the network. It has fully self-configuring multi-hop routing over heterogeneous carriers, and it can carry data over any mixture of physical mediums and topologies. And there are mechanisms implemented now that means that low bandwidth networks can coexist with large high bandwidth networks quite efficiently. It has initiator anonymity, forward secrecy for all communication types, both for single packets and over links. We have signed packet delivery confirmations. We have a flexible and extensible interfacing system, authentication and virtual network segmentations on all supported interface types. So you can make both open and authenticated VLANs on anything, both Ethernet and packet radio, whatever you want. There's a nice range of APIs. You can have access to the raw packet APIs if you want that. You can easily, in a few lines of code, sequence transfers of arbitrary amounts of data. You can also, there's also reliable and sequential delivery with the channel and buffer APIs that's similar to TCP. And really nice for developing applications a request and response mechanism is built in. So you don't need to like bootstrap something like an HTTP server on top of this just to get the basic request and response functionality. That's built into the stack as well. And you can use it over more or less anything. So this obviously requires that you create applications that are using this stack, because you can't just throw IP over this. It is a completely different stack. So do we have anything now that's actually useful? This is still early days, but we do have quite a few utilities that works exceedingly well over Reticulum right now. Of course, we have a system-wide routing daemon called RNSD, which handles all of the routing and interface configuration and handling, all of that stuff. We have fully interactive shell, similar to SSH, but this will work over very slow connections as well, reliably, and is fully interactive. We have basic management utilities, similar to ipconfig and iproute and ping. And we have identity management and encryption utilities for offline handling as well. We also have basic tools for information sharing, such as file transfers, file servers, and file drops. We have applications that allow hosting simple, low bandwidth pages that can be dynamic applications, such as forums, news aggregators, and proxies to other systems. And very interestingly, a universal messaging protocol called LXMF that provides both short-form, long-form messaging in a completely self-sovereign and secure manner with several different user-facing clients implemented. And it's also very easy to hack this protocol and just write your own implementations or bots or services or whatever you want. And one of the nice things is that it seamlessly roams between networks. So you can use this actually for day-to-day communication on your phone, on your Wi-Fi network, and connect to other people around you. And you can also just like bring it out into the mountains with a LoRa radio or a VHF radio and still be able to reach those same people. So it's not like you don't get this kind of walled, closed system where it's only the people that have the same hardware as you, because it can interconnect between all the different supported interface types. So just a short rundown of some of the programs that people have implemented. This is Sideband. It's a messaging client, can do both text and voice messaging and file transfers, image attachment. It has you can write like bots. This is a weather bot someone made for it that can download satellite images and stuff. It has a fully featured telemetry system, so you can use this to like share location with your friends or monitor your server status or whatever you want. You can also implement remote control, and it's fully scriptable and plug-in extensible. Mesh Chat is another nice user-friendly client written by a guy named Liam Cottle, also using LXMF, interoperable with all of the other clients, of course. This one features also real-time audio calls, which is a really cool feature. And this works over LoRa as well, which is quite fun to mess around with. It also has a Nomad network browser, which is the lightweight page hosting system that I talked about before. And that leads us to the last of the clients. This is Nomad Network. It's a terminal-based client that has basic text messaging and also the ability to host pages that can be either just like static information or dynamic pages you can render in Python or PHP or compiled programs, whatever you want. So there's a guy who wrote actually like a Wikipedia hosting for this. So Wikipedia is available over Nomad Network now, which is quite fun. And if you find any of this interesting, please come and join us right in here in the critical decentralization cluster. We have a Reticulum assembly, and you're very welcome to come and play around with the system and learn how to get it set up on your computer, play around with the radio hardware and all the different stuff we can do with it. So totally welcome to come by and learn how to set it up. And that's all I had for you. So thank you very much.
Thank you very much, Mark. You know, real-time audio calls over LoRa is a sentence I am still processing.
Yeah,
so
it really shouldn't work, but it does, provided you have high enough bandwidth. But it uses the quite awesome codec 2 codec, so you can go to the like even about 1,000 bits per second. You can have real-time audio.
Okay, I will process this later. Now, do you have in the room any questions that you need processed? We will give you the microphone, so...
What a service. What actually makes this restriction of the minimal required bitrate? I mean, you say you need at least 5 bits per second, but
Yeah.
what does make it? I mean, generally you could just slow down everything. You can make IP over DAFs, which can be even less if you carry only a few.
IP kind of does break down once you get down under like 300 bits per second. I have actually tried it, but it's a good question, and it's basically a question of timing, because we could adjust the timing, like the timing factors right now, to go even lower than that, but that would also mean potentially much longer timeouts when you're on a fast connection. So it's really not so much the question of how low can we go. We could go arbitrarily low, as low as we would like to. But we also want to maintain that when you're on a fast connection, you don't have to wait for 5 minutes to know that a connection timed out or a link was dropped or something like that. So it's the difficult thing is to get the range right, where it's not completely inoperable in normal use cases. But if you want to, you can make your adjust the timing parameters from the source code, and you could go to like 0.00001 bits per second. Yeah.
Impressive. Any more questions from the audience?
Yeah, over here.
Ah, yes.
Thank you
Hello.
for the talk. I'm still trying to wrap my head around this routing, especially verifying secure routes, because I have this BGP hijack stuck in my head,
Yeah.
but this is not the case here. But can you explain the routing verification?
Yeah.
once
So
more? Thank you.
since every path announcement is one cryptographically signed, so you can't forge it from anywhere else. All routing nodes in the network can verify the signature and drop anything that's invalid. And two, they are universally unique, so you can't replay them in any way. And they can only be retransmitted once. So if you get a destination announced from somewhere you have that has already been processed, it will simply be dropped. So it's a bit more complex than that in the implementation, but it basically ensures that you cannot replay them or forge the paths from anywhere. So a destination announce has to come from the system or person who actually owns that address.
Question?
And furthermore, any node in the network is free to choose a path that they choose themselves. So if you have multiple potential paths to one destination, and one of them is not working, you can simply try another one. And since all of the communication from that point is signed and encrypted, there's really no way to you can't put yourself in the middle of it, so to speak. Does it answer it? Kind of.
Do we have any Signal Angel questions? Thank you. One more question in the room.
Thank you for your talk. I want to ask you, what routing algorithm are you using? And what are the limits?
So Reticulum is using its own routing algorithm. I can't put any specific name to it. I'd love to show you the full details of how it works. What was your second question? Oh, the limits to it. The limits are going to be basically limited to processing speed and how many path table entries you can store. But since they are very, very light, you can store about 50,000 path table entries in 1 megabyte of memory. It's not likely to be a problem in the foreseeable future. And of course, you don't need to store everything in active RAM. You can just store the most recently used or active entries in RAM, and then you can store the rest on the disk or something like that. So you can have networks that have billions of endpoints still within very reasonable limits of the hardware we have today. And of course, it's important to note also that not all nodes in the network need to know the full path table or all of the destinations that are here. Any client on the network, like only routing nodes need even to have to store a destination table. So, and even those don't need to have all of them in either memory or on disk, because they can be requested dynamically when they are needed. So if you only have some specific amount of resources, you can simply limit the storage size of your tables to that. And as long as there's some way in the network to obtain the information when you need it, it's still going to work.
Question here in the front, right? I'm just going to give you mine.
How do the nodes learn about each other? So I have two nodes with some radio link potentially between them.
Yeah.
How does one node knows that there is another node that I can use for routing around me?
Yeah, that's a really good question. The strange answer is they don't, because all routing nodes are essentially transparent. So no devices have any addresses or any real presence on the network, but the routing nodes themselves will propagate the announcers from the actual destinations that now live kind of in the application layer instead. So the only knowledge you get about the routing nodes in the network is like a hop identifier that is appended to the destination announced when it is rebroadcasted. So you can specifically target one particular router instead of another. So the routers themselves actually don't talk with each other or coordinate. So you don't waste bandwidth on that. They are essentially transparent and passive.
Any more questions? I think I see a hand in the back.
Hi. So let's say I have an existing application that runs well over TCP, UDP, whatever you have. Can I commit the sin of running this over Reticulum?
You definitely can. I mean, theoretically, you could just write some kind of little wrapper that will push your IP traffic down through Reticulum, get it out in the other end, and you have like a socket in the other end. I wouldn't recommend that approach because it kind of misses the purpose of all of the efficiency and all of that. The best approach, I think, would be to simply write you have some kind of data in your application that needs to go somewhere else, and give the users an option of choosing to use Reticulum. Then you just write it probably won't be much more than like 20 lines of code to get that using Reticulum instead of IP, or even at the same time. So it's really quite easy to retrofit existing IP applications to use Reticulum instead.
Then we have another audience question.
Thank you. Meshtastic can store like 100 nodes on the device. How many nodes do you think you can save on a micro Reticulum node?
On a micro Reticulum node, like so on an ESP32 or something like that.
Yes, on ESP.
So most of those boards have around like 4 or 8 megabytes of memory. That's realistical, right? So you could potentially have like still having free RAM to do the rest of the stuff, probably around 100,000 destinations, which is going to be way, way higher than you're realistically going to service in that bandwidth anyway. So I think that's quite doable, quite realistic to do. If in some like weird scenario you want to be able to service more destinations than that, like only from such a small device, you could plug in an SD card and store the rest of the information in a SQLite database or something like that on the SD card. That would be possible, I'd say.
Do we have any more audience questions? They're in the back.
How do you address congestion?
So, are you talking about like congestion at the routing layer, or congestion for announcing the destinations, or just general traffic congestion?
But both.
Right. Okay. So, good question. At the layer like the destination announcers and the routing, there are mechanisms built in for limiting the amount of upkeep traffic, which includes the destination announcers, to by default 2%. And you can obviously reconfigure this if you want to something that's more suitable for your own topography. And in the case that limit is reached, the daemon will start dropping announcers from things that are further away. It'll start prioritizing nearby destinations or requests from local devices to get to be able to communicate. So, and in terms of general traffic congestion, if there's only one path towards something and you would try to shove more data down that path than is available, there's not really any way to avoid that fundamentally, other than trying to, block off some of the traffic in one way or another. But that being said, Reticulum works quite a bit differently than TCP, for example. In the TCP IP world, everything is very much center-oriented. So you get a socket, and you can just shove whatever data you want down that socket. And Reticulum works in a more receiver-oriented way. So if you want to send some data to a destination, the process is that you actually send a very small announcement packet to that destination saying, I have this and this amount of data I want to send to you. And the receiver will then be the one in charge of requesting new chunks from that data you want to send to it. So in the case that the network starts to get congested and the transfer fails for whatever kind of reason, you will have that the receiver will simply stop actually asking for more data. And it's not a perfect solution, but at least it alleviates some of the concerns. Yeah.
So we are almost at the end of the time. However, first, do we have a Signal Angel question? No. Then I think I have one here in the front, but you already had a question. So if there's anyone who's new in terms of questioning, I would put you in the front, but it doesn't look like it. So it's going to be you.
Maybe I misunderstood something, but I had the impression at some point that you have options to do packet switching, but you also have some kind of option to do a circuit switched networking. Is that true? So you can choose on which circuit, which trace, which path you want to send the data down.
Yeah.
Can you tell us a bit more about that?
Yeah, sure. So, yes, potentially you could do a completely packet-switched networking. This is possible right now over the raw packet API, but currently the link API will always be circuit-switched in that once the link has been established, for the duration of that link, packets will follow that specific path, right? So, and you, the protocol itself will support being able to route things over different paths. But this is not implemented in the current reference implementation. So that's a feature that would be interesting to look at in the future.
Thank you very much again, Mark, for this beautiful presentation. It was very interesting, very educational.
Thank you very much.
And come on, give him another applause. I know it's late, but...
Thank you so much.